guest who's volunteered to take some time out of his busy life right now to come talk to us. Juan was a student of mine a couple years back. I don't remember exactly, but he had me for what, 161 and 163, I think.
Yeah.
And yeah, so he got a lot of whoop ass dropped on him back then, and he's now let's see, you did an internship at Adobe, right?
Yeah.
And then
Adobe and VMware.
and you're a CS major, so all of your CS questions, this is gonna be a great time for all the CS stuff. And then where are you working now? I forgot already.
Yeah, I'm currently at VMware in Palo Alto, but since the offices are closed, I'm in San Jose working from home.
Right on, right on. And so with that, maybe do you want to just start by telling us a brief, like a story of Hancock and the transition, and maybe just introduce yourself a little?
Sure, yeah. I put like some slides together really quick. So
Yeah, yeah, go for it.
share it really quick. Oh my goodness. Classic technical issues. Let me
Yeah,
see.
it's always, yeah, the Zoom that I have is like Zoom on steroids. There we go. Oops.
I don't know where it went. Hold on, it just disappeared. Sorry guys, give me a sec.
Yeah, yeah, you're good.
Okay. All right, I'm just gonna do.
There we
Okay.
go.
Let me move it back over here.
And I
Okay.
believe the version of Zoom I has allows you to annotate if you want. So if you want, you can look around in there and see if there's an annotate button somewhere. But
Can everyone see my screen? It should just say hi.
yes,
I'm on. Okay.
got it.
Sorry, it looks a little off. I don't know. This is okay. So if you guys have ever done a presentation in George Stats class, this is what you should be avoiding right now. I don't know. I swear when I was on this earlier, it didn't look like this.
It looks fine. It looks great.
Let me go ahead and present again, and let's see if we still get it. Okay. So
if only he said that when you were grading us.
So I put these together super quick. Trust me, if I was doing an actual presentation for George Stad's class, I would be a lot more paying attention to detail. But I'm Juan. I was at Hancock from 2014 to 2017 as a CS major. I took George Stad for 161 and 163, got my ass kicked thoroughly, but it was awesome. So I'm just here to talk to you a little bit today just about my journey from Hancock, transferring in and then getting a full-time job. This might be boring for non-CS or software engineering majors, so I'm sorry if it is, but I hope you can grab something from this. But for those of you who are computer science or software engineering majors, feel free to ask me any questions. The presentation will be kind of short. I'm leaving most of the time at the end for questions. So again, I started at Allen Hancock in fall 2014 as a computer science major. I had previously gone to San Francisco State for a couple of years before this, but that's a story for another time. If you're interested, we can connect later and we can talk about that. But I'll just start at Hancock. And then in my summer in between transferring from Hancock into San Jose State. Yeah.
Are you changing slides?
No, it should be the same.
Oh, okay. Okay, good. Sorry, I didn't know if you were changing. My bad.
It's the little timeline thing that's animating. I didn't want to overwhelm you with all the information at once, so I'm doing one piece at a time.
I'm still seeing the hi, I'm Juan slide.
Oh, weird. Okay, give me a sec. How about now?
There we go. Got it.
Okay, cool. So in the summer, in between Allen Hancock and San Jose State, I did a program called INCAS. I heard about it through Dom. So I don't know if they're still going to be doing it this year. But it's basically just an academic competition to where you do like an online class, and then the top performers from that class get invited to NASA to go on site to do another like Mars rover competition. But I think that was pretty helpful. The reason I put it up here is because it was interesting and it helped me get my first internship. So if INCAS is still around, I would recommend looking into that. I would ask either Dom or George Stad about it. Hopefully they're still doing it. Let's see. And then next, when I came back from that, it was only a couple weeks long. So I interned at Rabobank, which is now Mechanics Bank in Santa Maria. So I was technically, my title was Corporate Security Analyst Intern. However, throughout the whole internship, I probably looked at 2 Excel sheets the entire time. I really did nothing there. And it was my first internship, so I could have been more proactive to try and find work. I think that's what you should do in your first internship, but I didn't know. So I kind of wasted my summer there. At least I got paid for it. But again, that kind of still helped me to get my first real internship afterwards, even though I didn't have really anything to say about it. So after that summer, I started at San Jose State in fall 2017 as software engineering major. So when I went to San Jose State, it wasn't my first choice. Cal Poly SLO was actually my first choice. I didn't get into Cal Poly for computer science or software engineering. I was like super crushed about that. And I was really bummed. I had talked to Jorstad, I talked to Dom, I talked to Pavone, I talked to Wagner. I was like, how am I ever going to be successful after I graduate if I didn't get into Cal Poly? Like everyone around me got into Cal Poly, and I was like one of 2 people that didn't. But I guess I'm living proof to say that you don't have to get into Cal Poly to be successful or to do what you want to do. So trust me, if you don't get into your first target school, just know that that's not the end. I was just distraught about it, and I still turned out fine. So after my first year at San Jose State, I got an internship at a company called VMware in Palo Alto. That was a super cool experience. It was like my first real tech internship. It lived up to everything that you see or hear about. It was just really, really fun. I got to work on some pretty cool tools that help the engineers there. And then after my second year at San Jose State, I got a return offer to go back to VMware as an intern, but I wanted to kind of see what else was out there. So I was able to get an internship with Adobe for that summer. And I got to fly out to Seattle, hang out there, work there for the summer. And yeah, I did some more kind of like data analyst, data science stuff for Adobe. That was really fun. But I found like data science is not my thing. I don't really like working with data. So then the next summer was coming time for graduation. And I got a full-time offer from VMware to come back as an engineer. And I got a full-time offer from Adobe to work there in Seattle. But I just kind of got a better vibe from VMware. Seattle is really not my thing. It's super outdoorsy there, and I'm not really an outdoorsy kind of person. So I just didn't feel like I was a good fit for Seattle. So I ended up accepting at VMware, where I'm currently at. I started back in June. I'm a full stack developer there. So if any of you are interested in full stack, that's kind of like what I'm doing now. But yeah, that's kind of like my general journey. There's a lot of details that go into each part of this, but in the sake of time, I'm going to keep moving forward. We can always connect after, and you can ask me anything you want. So I'm going to go ahead and open it up to questions. If anybody has immediate questions, I kind of have some stuff prepared in case nobody has questions, but I'll open it up to you first.
And I'm just going to get the screen share and get you back there. And let's get, oh, whoa, where'd he go? Where is he? Oh, there he is. Ah. Oh, man, always something. Oh, where'd you go? Sorry, I'm looking for you on there.
Maybe if I talk.
Yeah, you talk. I'll shut up. I'll just go back to gallery view there for a minute. All right. So, oh my gosh. So questions for Juan, and you can stick them in the chat. And I obviously am wondering like how much you use Python on a daily basis and what that's like and how your CS prep served you. So how well did Hancock do preparing you to succeed, and how much Python do you use?
So first, I guess Hancock did as good of a job on its own as it could. For computer science, it's a really competitive industry. So there's a lot that you need to be doing outside of school, which I just didn't know about. So like when I transferred into San Jose State, I didn't realize that that's when the internship hunt starts. So like right when you transfer in, companies are already starting to hire in that August. And since you're going to be transferring in typically your junior year, that's like the prime time to get your first real internship. So I had no idea. So I was just, focusing on school. And then January comes around and I'm like, oh shit, like I need to start looking for an internship because everyone around me has one. So I guess like there's a lot of work that has to be done outside of class. So maybe just do your own research as to like, or, you can ask me, I'll share my contact information. But yeah, I think that there's a lot that needs to be done outside of class. Maybe even talk to Wagner about like what kind of things you can do to prepare. That would be a good first step. And Python, I think, is probably one of the most important languages right now to know. I'm a full stack dev, so I use Python on the back end, but I use Python all throughout my undergrad because it's a really easy language to pick up and it's super fast to write what you want. So like if you're doing something in Java versus Python, like just writing it in Python is going to be a lot faster. So for interviews, people typically use Python just because it's the easiest and fastest language to do it in. So I would highly recommend using Python. It's one of the more popular languages right now alongside JavaScript. So yeah, Python's super important. I use it every day in my work. I used it in my first internship with VMware was like strictly Python. And my second internship was more like SQL database kind of stuff.
I gotcha. I see a couple of questions here in the chat. One is, so from Corey, are you able to see those, Juan? What are some recommended ways to learn about cloud computing and other VM related subjects?
Yeah, I think VMware they have like some technical trainings, so you can look
what does VM mean? I don't know.
Virtual machine. So,
okay.
Yeah, VMware kind of got its start based on like virtualization. So that's kind of like what they're all about. So I think VMware has a lot of like technical education that's available for free. So I would just Google it and poke around their website. I don't have a link for you. Maybe I should have been more prepared for that. But yeah, I would look around on their website, and then other sites like Udemy or like Coursera, I think, something like that. I think those will be helpful resources. I think the Udemy classes are mostly paid, but I think VMware has some free stuff.
What about MATLAB? I see Nate Dogg asked about how much did you use MATLAB, or do you ever use it? I'm guessing not much.
Yeah, as a software engineer, typically not at all. I've never learned MATLAB. I never touched MATLAB. I think that's more for like the electrical engineering, mechanical engineering kind of disciplines.
Yeah, definitely. The engineers use that all the time, right? So there's another one.
Say AI, like some terminology, but what I used to start. So for AI, I would just Google around if you're interested in doing a project. Just like Google simple AI projects, things like that. You'll find probably a bunch of posts online about it. I personally have never like delved into AI, but they do have AI classes at San Jose State. I'm sure they have them at like Cal Poly or Cal, wherever you're planning on going. They'll have intro to AI classes. I know that AI and machine learning are like very math, probability, and statistics heavy. So that might be a good thing, because I know the intro to AI class, they use a lot of math and probability statistics. So yeah, that could be somewhere to start, I guess.
I gotcha. So obviously I make students give presentations and such. What is your reflections on that experience? Did I make you give some, I think?
Oh, did you? Yeah, so learning how to do proper presentations Jorstad style is going to save your ass in the long run. It really will. So as long as you pay close attention to how Jorstad asks you to do presentations, it'll be smooth sailing for you during your undergrad and even into your full-time work. So like even now I carry the same kind of sentiments when creating a presentation. Today wasn't the greatest example. So I'm sorry of that. I should have more prepared. But yeah, presentations, you're gonna have to do them all the time. You're gonna have to do them almost every single class. You're gonna have to do it in your internship. You have to do multiple presentations. So just knowing how to do a proper presentation without many hiccups is gonna be super important. So I would say take that to heart.
Gotcha. Other questions from the galley here. Sorry if I'm taking, I see.
Yeah, I start standing. You can see us having to sit in front of a screen for hours. Is a standing desk the way to go instead of sitting? I guess it's really your preference. I like standing every now and then, and since it's work from home, most tech offices will have like standing desks that you can choose to use. I kind of got used to it, and I like doing it because sometimes if I'm sitting for too long, I start to feel a little tired or lethargic. So it just helps me to kind of get some blood pumping And I know there's some science that says it's good for you. There's some science that says it doesn't make a difference, but it's really your personal preference.
I'm going to find you. I'm tired of looking at that tiny little thing. I'm going to take the time to go through the whole 60 of us and find you. I want to see you big screen here. Sorry. Oh, there you are. Got it. Hey, all right. I have a question. So I always tell people about pair coding. How often do you do pair coding, and is there any best strategies for success on that? And is it standard in the industry?
Yeah. So, I mean, there is like the formal definition of pair coding where like some people may take it strictly to where you actually like follow all the steps and rules to like this idea of coding in a pair. But outside of that, even there's still going to be a lot of opportunities where you're working alongside someone else to debug a problem, or to ask how to use something, or to like work your way around a code base. So working with someone else in a programming project, especially during your undergrad, it's going to be something that you have to do almost for every single class. You're going to have to work in a group. So being able to do that, being able to work with other people around the same code base, using either like version control like Git or something like that is going to be super important. So yeah, working with someone else around code, super important. You're going to have to do it all through your undergrad, and you're going to continue to do it in your full-time position for sure.
Do you have any tips on like strategies that help you work well with others when you're coding in a pair or a small group of 3 or 4?
Learn how to use GitHub.
All right.
Yeah, learn how to use GitHub. I was so shocked when I got into San Jose State, and I learned how to use it right away because I was like, it just made sense. Like if you're using a group project, use version control. But so many people were so resistant to learning how to use GitHub. It made, like when I was in a group with people who refused to use GitHub, it was just such a pain because they either like texting you code and it's like emailing you code. It's like, dude, no, this is going to get so messy so fast. But I would say learn how to use GitHub. You're going to use it. It's going to be something that's going to come in handy all through your undergrad, and you're going to have to know it for sure once you get a full-time job. How does the workload in Jorstad's physics classes compare to your work now? So I would say that the workload in Jorstad's classes helps you to prepare for kind of like the worst case scenario. So it's kind of like all hands on deck. So it's never, in my experience, there was only one professor in college that I had that was Jorstad's level of work he was like the Jorstad of computer science. And that was awesome. That was so fun. Like I was ready for it. Students like always tend to shy away from that professor because they're like, he just makes it so hard. It's like so unnecessary. He's like crazy. But that's how you learn. Like you dive deep and you have to know your shit or you're not going to pass. And so I think that it really sets you up for success later on because it's not going to get much harder than that. And then even as a full-time employee, like it's a little bit different because it's not a class style where you have homework and things like that, but it helps you kind of know how to learn, how to ask questions, how to reach out when you don't know, or else you'll get buried. So it kind of teaches you a lot of good things along the way.
Interesting. Is there anything that like sticks out in your mind when you think about like, man, I wish I would have done X, Y, or Z at Hancock, or I'm really glad I did this while I was at Hancock?
Yeah, so I'll start with like, what are some things you're glad you did at Hancock? So there's a couple things. Applying for scholarships, the Allen Hancock Foundation, everyone should be doing that because that's easy money. Because it's like such a small pool of applicants just within Hancock. So you should definitely be doing that. No matter if you think you qualify or not, just go for it. Go to office hours. So when I took 161 with Jorstad, I wasn't ready for the workload. I barely passed. I think Jorstad gave me grace and I passed with a 70.0. And so like, I didn't go to his office hours very often. I just didn't know what to expect and how to step up. So going to office hours, when I took 163 with him, I basically lived in his office. I stayed there until 1 a.m. until the janitors would kick us out. We would stay next to his office. So I guess just go to office hours. It's super important. And Jorstad's super helpful. He'll try to help you as much as he can. And plus you can also work with other students who are in the office hours as well. Maybe they have the answer to your question. You have the answer to theirs, something like that.
That obviously is a little weird right now with COVID, right?
Yeah.
It's
yeah,
hard.
well,
Oh, go ahead.
Well, then that means there's no excuse, because all you have to do is log in to the Zoom, and like that's it. So you should really be there. And then the next one I would say is like know your resources. So like the STEM Club, Mesa, MEP, Trio, things like that. Make sure you're aware of what kind of support resources that are available through Hancock, because you never know when something happens. So like, for example, I was a member of Trio, and I would go there to print things because you can print for free. And I would just like do my homework there. And then one time my computer like just stopped working, and I was able to check out a computer through Trio. I forget exactly what it's called, but it's a Trio organization. I forget exactly what the club is called.
Yeah.
But yeah, just know what resources you have available to you, and utilize them if you need them. A next thing is look for local internships or job opportunities. So for example, the internship that I did with Rabobank or Mechanics Bank, I know that they love to hire Hancock students. So definitely check out and see if that's something that they're still doing, because they had a whole program where they were hiring like nothing but Hancock students for internships. So check there. And then there's like tech companies based out of SLO, because SLO is like a little tech hub. So, don't shy away from those. Don't think that they're only for Cal Poly students. Like, go for it. Put yourself out there and try. I think I applied to MindBody like every summer that I was at Hancock, and I got denied every single time. But it's worth it. You kind of like learn how to like deal with a rejection, or like learn what the interview process is like.
Going through the application and interview process is always good experience, right? The more you do that. Yeah.
Let's see. I know there's a question in the chat.
Yeah, let's see that.
Well, you've referred quite a bit to the work outside of class. Could you define that in detail a little bit more? Excellent question. So, for example, I think that is the intro to CS classes here taught fully in Java now?
I think so, yes. But I don't know. The students probably know better than I do.
Okay, because when I was here, like I think 111 was in C++, and then 112 was Java.
Yeah, I think he transitioned them all over to Java.
Okay. So you'll know Java, right? Like you'll know the 111 and 112 of Java. Then you'll transfer in, and then you'll have to take a class called Data Structures and Algorithms. And that's going to say like, hey, you need to know how to use the debugger. So like in office hours earlier, we were talking about the debugger. So you're going to need to know your way around your IDE or your text editor, whatever you're using. So that's not something that you're really taught in 111 or 112. At least when I was there, we weren't taught how to use a debugger. You're going to be expected how to know kind of like the ins and outs of Java. You're going to need to know Java a little bit more. So I think even the level that I was at in 112, I didn't know enough. So I had to do a lot of practice over the summer. And then even when I got into San Jose State, I got into data structures and algorithms, and like I got my ass kicked for like the first couple of weeks, because I was like, wow, I really don't know this much about Java yet. So a lot of classes in your undergrad, they're not going to teach you these things. They're going to expect that you already know it, or that you can teach yourself how to do it. So for example,
that's cruel.
It's cruel. But like, that's what, as an engineer, you do, right? You learn how to ask questions, you learn how to find information, and you learn how to like teach yourself basically. And so like, there's a series of classes at San Jose State called Software Engineering 1, 2, and 3. And for each one, you have to build a full stack application. So you have to do a front end and a back end, but they don't teach you JavaScript. They don't teach you the back end. They don't teach you anything. They just say, here's a team, build a project. And that's what you're doing the whole semester. You have to do that over and over and over all the time, but there's not a JavaScript class. There's not like this, how to build a full stack application class. So that's what I mean by work outside of class, is they're going to expect you to do certain things, but they're not going to teach you how to do it. They'll be there to like guide you a little bit, but there's no like formal education on these things. And like I'm saying, so like when you're Python is the most popular language for interviews, and that's not something that I was taught by a class. It's something that I literally just holed myself up in my room for a week and watched videos and learned how to do it myself. So that's what I mean by work outside of class. It's kind of expected, even in industry right now. Like for my internship at Adobe, they said that I needed to learn C++. I didn't know. I took 111 in C++, but that was like very basic. But for my internship, they said, okay, so we'll need you to know C++. It's okay that you don't know it now. Just learn it before you get here. So that's what I'm talking about. Like, it's kind of, that's how the industry is. Even for my full-time job now, I have to learn Angular, Django, and the Django REST framework. And they said, it's okay that you don't know it now, just learn it by the time you get here. So that's kind of just how it goes.
So I'm just curious. I mean, this seems like the bosses and the teachers can do this because there's so much demand for this education and these jobs. They basically can screw you over and dump all this work on your plate and give you no money for it or no credit for it, right?
Yeah, I mean, I wouldn't paint it in such a malicious way.
I would.
It's just kind of like the expectation of the field. It's like, it's highly competitive. So if you're not there to step up to the plate, someone else will be.
Yeah, right, exactly. Now, all this said, are you happy with the choices you made in terms of choosing this as a degree? Are you satisfied that it's going to give you the income and the lifestyle and the life you want?
Oh yeah, definitely. I wouldn't change a thing.
All right.
It's because, as an engineer, you love to solve problems, right? Like that's what you like to do. There's a problem and you solve it. So there's no shortage of kind of like learning and stepping up to the plate here. It's as you have to do something that you enjoy. And so I really like being able to do the research, get stuck, get frustrated for a couple hours, go on a walk, figure it out, that kind of thing. That's what this is. And if it's something that you like, then yeah, for sure. I wouldn't have changed anything.
So I see that question, differences, software engineering, CS.
Okay.
And then maybe after that, because I do know they have a quiz coming up, we should probably call it pretty soon. So
okay.
Maybe we'll make this the last question and we'll let you have a takeaway point after that.
Right on. What are the most distinct differences between the software engineering and CS majors? Good question. So there is a difference between software engineering and computer science. The way that I like to say it, don't quote me on this because I'm sure if you like repeat this somewhere else, someone might bash you to bits about it. But the way that I like to see it is kind of like software engineering is to mechanical engineering what computer science is to physics. So computer science is more theoretical. It's more the theory and the research of computing. And software engineering is more the practical, hands-on, how do I build software and how do I like work with a team to build this in a company. And so there's like that difference there. Typically, if you're interested in more of like an academic or research, like if you want to do master's or PhD, CS is kind of like the route. But if you want to just get into the industry, like know how to just hit the ground running, just go be a software engineer right after you graduate, software engineering is kind of that route. But you can do that route also with CS, or you could do that same route, the CS route with SE. So it's like, it's pretty interchangeable. Like I would, depending on what your target school is, look at the curriculum for each major and compare where the differences are. They're probably going to overlap for like 90% of the coursework. And then there's going to be just some variation in electives or something like that.
Do people get hired as often with a CS degree as they do with software engineering, or are people coming out like, so this is what I remember, like people with a physics degree, they can learn anything and they're great, but people don't hire them because they're not an engineer with a certification already in place. Yeah. Is that somewhat similar in CS, or is that not the same?
Not really.
Okay.
You can get a job as a software engineer with a business degree. It doesn't matter. It really depends. Like, do you have the technical chops? Do you know how to code? That's really it. Go ahead.
What do they do in the interview to quiz you?
Okay.
Job interview.
I know I'm running short on.
No, I'd rather talk about this.
Short on time, but
I'll just tell them something's not on the test. They'll like it.
Let me try to share my screen again. Okay, can you guys all see this?
Yeah.
Okay, so this is an example of an interview question that I was asked by Adobe. This is actually the exact question that they asked me. So this is the kind of questions that you should expect in an interview. So it's basically like a puzzle. They give you a programming puzzle and you work with an interviewer within an hour time frame. It's usually, so an interview is like an hour. The first 15 minutes is like pleasantries, like tell me about yourself, that kind of stuff. Then 45 minutes is dedicated to the technical problem solving part, which is this kind of stuff. So let's say they'll give you this question and then you'll be in front of a whiteboard, or since it's going to be remote interviews, they'll like have like HackerRank or like some type of code that you'll both be viewing at the same time. And so they'll give you the problem and then they'll watch you code. If it's in person, it's going to be on a whiteboard. If it's over like virtual, then it's going to be like
your screen share
through a web browser.
Yeah.
And so they'll ask you to solve this problem. You have to do it live in front of them.
That seems intense.
Yeah, there's an art to it. That's what I'm saying by like, you have to do work outside of class, because there's not a class unless you go to like Stanford or Cal. They do have interviewing classes, but most colleges don't have classes that teach you how to do a technical interview.
It's almost like that. It almost looks a lot like an oral exam, doesn't it?
That's what it is. That's exactly.
Oh, they have that in this class. Yeah, thanks for selling that for me, dude. Yeah. Sorry, Joy does not like the oral exams, but yep, it's real life, right? That's being able to communicate about technical issues. Yeah. Okay. Sorry. I got distracted there.
Okay.
Sorry. I forget where we were. My bad.
So I know there's like some questions in the chat, but there's a couple things that I really wanted to go over, because I was like,
yeah, do it.
If I was a Hancock student getting ready to transfer, what would I want to know? And I put together one slide that has that information.
Let's check it out.
Okay, so I just want to share it with you guys really quick. I'm sorry if I'm taking up too much time, but
no, this is great, dude.
Okay, can everybody kind of read that? Is that big enough?
Yep.
Okay.
Yeah.
So this is information or advice that's specific to computer science or software engineering students. So like I said, the internship hunt starts right away. Large companies like Google, Facebook, Apple, they start in August. So whether you're on the quarter or semester system, it doesn't matter if you started school, that's when the interviews start. So typically, if you're interested in getting an internship at one of these large companies, you want to apply there first, because since they're larger companies, they move slower. So the interview process takes a long time. I interviewed with Google twice, and for an internship and for a full-time position. And each time the interview process spanned over a couple of months at least. And so you want to start those first. So like right when you transfer in, that's the time to start going, because people are starting to hire already. And then the smaller companies, sometimes they'll start around August, but typically they'll start around October, November, and they'll hire a little bit later. But the larger companies like Google, Facebook, Apple, they're going to be done hiring by December. By the holidays, that's when they want to have all of their seats filled. So if you're looking for the Google, Facebook, or Apple, and you start looking in January, you're shit out of luck. Like you're not going to find much. But the smaller companies will still be hiring around that time. Like I said, also there's an art to the technical interview. There's a book called Cracking the Coding Interview that details everything about the technical interview. I would highly recommend either buying or like finding that book online. It can be found online. But I would definitely like look into that book. It's basically like during my undergrad, it was my Bible. Like I referred to it all the time. The next thing I would recommend is learn Python. So since you guys are doing that right now, it's super important, just because technical interviews move fast. And so you need to be able to write a program within 45 minutes. And Python is the most relaxed language that will let you do that quickly. So Python is a super important language to know for interviews. And it's also probably the #1 or #2 most popular language right now. JavaScript is also really cool as far as it's a popular language, but I wouldn't choose to interview in JavaScript. There's a website called LeetCode. If you've heard of HackerRank, LeetCode is something that's it's the same thing basically. So the question that I showed you earlier, this came from LeetCode. So if you Google LeetCode 48, this question will pop up. So for those of you who aren't familiar, it's basically just like a website where you can type in your code and you run it. So they give you a bunch of, they give you questions, and then you can keep answering the questions and solving them as you go on. And they rank them by like easy, medium, hard. Sometimes they'll have questions sorted by company. So you can ask questions that Google has previously asked interviewers or interviewees. So I would practice that just to make sure that because those are the same kind of questions you're going to get in an interview. So if you're pretty good at LeetCode and stuff like that, you'll do pretty well in an interview. The next thing is start a personal project. Since you're transferring in, having I would say this summer in between when you transfer to your university, take the time to do a small personal project. It doesn't matter what it is. It doesn't matter if it's like, the newest tech in Silicon Valley, or like the hottest new startup. Like it doesn't have to be that. It can be something that already exists. The point of having these personal projects is if you don't have an internship, Then recruiters look at, hey, do they have any projects? Like, are they excited about programming? Do they know how to build a piece of software? Do they have the experience of kind of like going through this stuff on their own? So if you don't have an internship, the next thing they look for is personal projects. If you don't have an internship, you don't have a personal project, you're in the back of the line. So I would say look at a personal project. So for example, one of my old roommates, something that he did is one time I was out and I texted him. I was like, hey man, can you call me and pretend that you're drunk? Like I really need to get out of this social situation. So I'll like say, hey, my roommate's drunk. I need to go pick him up. And so he did that. And then when I got home, he was like, hey, you gave me a really great idea. I'm going to build a website that you can say what time do you want me to call you? And then it just gives you an automated call with a random drunk person's voice. So you can get out of a social situation. And that wasn't something that was new, right? Like it had already been done. Sure. It had already been done. And so but that wasn't the point. The point was that you took the time to learn something on your own. So it doesn't have to be something that's new. It can be something that's been done before. And it could be small. It doesn't matter. It doesn't have to be big. It can be super small. Let's see. And then discover the primary languages or technology of your target school and get familiar with them. So for example, San Jose State uses mostly Java. So the intro classes, data structures and algorithms, object-oriented programming, they all use Java. And at Cal Poly, they use mostly C. So my brother actually graduated from Cal Poly as software engineering. And I asked him like, hey, what would you recommend? So he said C and learn the Unix terminal. He said that would be really helpful. So for example, if you're going to like Berkeley or Stanford or whatever, CSU Northridge, like it doesn't matter, whatever. Like try to find a way to reach out to someone who goes to that school, either through like the typical way that I used is through Reddit. You can just go on Reddit, like the school subreddit, and just try to get a hold of someone. And then you could just try to figure out, or like look at their class offerings and just see what languages are used the most, so that you can use your summertime to kind of brush up on that so you don't come in and absolutely lost. Okay, and that's basically what I wanted to throw at you really quick. Here's my contact information. Feel free to screenshot it, whatever. Send me an email, connect with me on LinkedIn. Like I'm totally down to help answer any questions. If you want me to review your resume, whatever, like you could use me as a resource. I'm totally open to that. Ask me anything. Nothing's off limits. Okay.
You are the man, Juan. So, hey, everybody, let me, whoops, there we go. So let's go to the gallery. Hey, everybody, give Juan some love, will you? Give him a thumbs up or something, or these cheesy Zoom buttons. All right. Oh, I'll give you the shocked face. How about a birthday party?
Oh, wow.
There you go. I'll give you some real love there, Juan. Hey, Joe, you got a question? So go for it, Joe, real quick. Just unmute if you want. That was really great, Juan. I appreciate it. Oh, he's throwing it in the chat there. Go for it, Joe.
No.
Oh, I see. Just
my bad. I was just putting, yeah.
Like the hand of Sauron. I got you. Yeah. That's cool. All right. So, Juan, I really appreciate that. And those of you that aren't CS, I hope he gave you some good things to think about, even if you're not CS. But I told him to try and do CS and software in particular. So I asked him to do that. Thanks again, Juan. And I guess I'll talk to you later. Well, they have to do a bunch of physics calculations now.
Cool. Sounds good. Hopefully I took away some of the time from your class, so it's you have less of physics to do now.
Right on.
Like I said, feel free to reach out with anything. Please use me as a resource if you need to.
Okay. All right. Thanks, Juan.
Yeah.
So I'm going to go ahead and get into the class and let me get some files open. So that was really awesome. Hopefully you guys got something out of that. And don't be shy. That's our second guest speaker. I don't know why they're doing that. They're just being nice. So take advantage of that resource if you can think of a way to do that. And give me a second while I open up some windows here. Let's close this one. Let's see. So we're going to start up here in chapter 24, and we're probably going to start up at page 77. If you want to get your book open, the workbook to page 77, practical applications of the plots. I'll do a screen share in just a sec.
What is that behind you on the whiteboard?
Oh, that's chapter 27. We'll get to that in a few weeks.
Oh.
Yeah.
It looks like fun.
3 class or something?
No, that's your class.
So what's it doing up there?
There's a student working ahead.
Oh,
Yeah.
okay.
So yeah, it's fun. Well, it's resistors, and actually in lab we'll start that next week. So we'll start doing the voltages in lab next week and stuff. So, yep, cool. All right, good question. Sorry about that. And then we are probably about right here. I think we did that already. Did that already. There we go. We're going to start right here, and let me check the chat there. I'll let them tell you, or stick around in office hours and you'll see. All right. So, all right. I don't want to put them on the spot. Well, yeah. So, all right, let's get into it. All right. And let me get my board ready to go here. So, where are we? Let's do this too. Okay. Yeah, I don't understand it, Ryan. What's the story?
It's from Monty Python and the Holy Grail.
Believe it or not, I'm like not a big Monty Python fan. Everybody thinks I would be.
It's so good.
I'm like, oh, what's this? Oh, yeah. Hey, man, I'm into Fletch and Big Lebowski. That's my scene. All right, that and Alien and vampire movies and stuff. All right. So, all right, let's see. Where are we doing? Okay, let's focus on this. So, to be clear, in case you're worried about us running out of time today, we are not going to run out of time today. We need to get through this page. And I think after that, I'll make a deal with you, since you guys got to listen to my speaker. I'll make sure this is not on the quiz, and I'll double check right afterwards. I better check this and make sure it's not. So I'll make sure this next content is not on the quiz. And then it may appear on the final exam, so we should still talk about it and you should still do it, but I'll make sure it's not on the quiz this week. That way you can kind of de-stress a bit. All right. And so our goal today is to get through this page, and then we can do any other problems from the rest of the chapter and do extra practice. So that's our goal for today. Make sure we understand this. So I want to be clear here. We're looking at this equation. E is negative the gradient of voltage. Now, since we're not allowed to do 3D vector calculus in this class, we're going to simplify that to a 1D problem, which essentially looks like this. If everything is constrained to move in one dimension, we could change our partial derivatives to totals. Maybe you noticed that. And then in practice, what does this mean? The electric field in the x direction, so left, right, is equal to negative. And let's do that. Let me do that in some other color so it's really emphasized. It's minus. That's the minus sign that came from the definition here. And the reason that minus sign is there is so that electric fields point from high voltage to low voltage, not the other way around. It's minus the slope of a V versus X plot. So notice here, this slope is negative, right? We have a negative slope. That implies E sub X is positive. So that means the electric field is positive. Now this is where things get tricky. Okay, and so I want to keep talking about this region right here that I've circled. I want to keep talking about that particular spot. Oops. Okay, and so now I want you to imagine we put an electron or a proton right here. If we put a charge here, the idea here is imagine the charge is a marble. This is a little bit different than chapter 8 when we did that in physics 1. So the charge, if it's a plus charge, the logic from chapter 8 is exactly the same. Plus charges go with the electric field, and it would go this way. Think of that as a marble rolling along the track. Now, where this gets a little bit sneaky is, what if I put a negative charge on the track? If I do a negative charge, negative charges move opposite the electric field. That would tend to go this way. Or you could think of that as flip the graph upside down in your mind, and it's like an air bubble floating towards the top, right? So electrons are going to go opposite the electric field, which means opposite the slope. And yeah, and so there, okay, point being here, we've got a lot of minus signs. We need to take our time in this, and our conceptual check will be positive charges will roll on these potential plots just like a marble on a track. They're going to slow down when they, whoops. Positive charges, doing this another way, let's say I start with a positive charge right here and it's moving this way. It's going to slow down as the voltage goes up. When the voltage is constant, it's going to move at constant speed, and it's going to speed up as the voltage goes down. And because there's a net change in voltage from here to here, there's going to be changes in the voltage or changes in the potential. We can see that there's different issues that might show up. There's different delta V's in this case. You have to make sure the electron has enough speed to get over the big voltage. Otherwise, it won't make it to this final voltage. And electrons are exactly the opposite. Electrons are going to speed up as they go to positive voltage, right? They're going towards a positive plate. Whoa, that's intense. Let me pause and see if there's any questions about that.
Yeah, I got.
Can you just say that one
got
more
a
time?
question. I just don't know how to
Okay.
ask it.
Okay, let me say this one more time. And again, we're going to do these problems over and over again. But so let me just explain this one. If you put a plus charge right here and you release it from rest, plus charges go to lower voltage by that's their natural tendency. If I put an electron right here, electrons tend to go to higher voltage. So if you took a plus charge and a minus charge, put them at the same spot, release them from rest, positive charges will tend to move on the graph until they get to a lower voltage. Negative charges will tend to move until they get to a higher voltage. Did that, okay, so now what was your question? Is that, and try to say it, and I'll try and help you phrase it if you're not sure. All right. Okay, let me show you something else here. One of the things that students really get confused on, and I hammer on this in 161 in chapter 8, remember that we are not actually putting charges on this curve. We are not doing what I'm drawing. You can think about it that way. And you could think about this, if this was an electron, it's going to negative voltage, or sorry, this is an electron going to more positive voltage, it should speed up. And then here it will go at constant speed. Now you have an electron. If it was an electron and it's going to a lower voltage, it should be slowing down. Now, what in fact is the electron doing? The electron starts right here and it's not moving up and down at all. It's moving left and right and things like that. And so the electron is moving horizontally. The marble analogy helps us think about the speed while it's rolling strictly in one dimension, left or right. So the marble is not going up and down. It's moving left and right. That's the charge is moving to different X positions. As it does that, you imagine what would happen if it was trying to roll to a higher voltage. It would speed up. All right. Yeah. How about we start working out this problem? Let's just start, and I'm going to draw it on my board, and that way we could talk on the whiteboard, and I don't have to keep doing the screen share crap. So give me just a sec. I'm going to write this plot out a little bit, all right? And so I'm going to basically start with 24.30, and it's not going to make a lot of sense. But by the time we get through 4 of these, you can do any of them, okay? And this is on your quiz, guaranteed somehow. What did I say? Nanometers? Ugh. Here we go. Millivolts. That's the first thing you better watch out. On the quiz, everybody's going to have different prefixes. So you better watch out for nano, milli, micro, etc. Okay, millimeters, could be nanovolts, could be microvolts. Everybody's going to have different prefixes and stuff like that. So milli, micro, and nano are the most common that appear in these types of problems. So milli, micro, and nano. So now, okay, we got 20, 40. Go ahead. 20, 40. And I'm just drawing and catching up, okay? I'll move the board in a minute. All right. So let's get to the whiteboard. Now I got to find me in this mess. There we go. All right. So that's my attempt to draw that graph. It's not very good, but you get the idea. And so I'm reading this question, and we know one equation right now, and we're going to try and use that and learn a lot of information. So what do we know? We know that the electric field in the x direction is equal to negative dv dx, which means negative slope of v versus x. That's what we're going to try and use. I suppose I should mention a couple of other things that we know. We know the following pieces of information that also end up being very useful in these types of problems. We know that the force in the x direction, how is that going to relate to the electric field? If I wanted to get a force and I have a charge that has charge Q.
Multiplied by another charge.
Yeah, but if I know the electric field from the plot and I know the charge, there's another way. That's a good thought. You were right. It's
QE.
Yeah. So this is another way to do that. And so the way that you're describing it was excellent if you have 2 point charges moving around. And so this is what you want to be thinking about now. We haven't used this that much until now. The idea is we could figure out the electric field from the plot and then multiply by a charge, and that would tell us about the force. That's cool. What about potential energy? If I want to get the potential energy of something, that's equal to Q times the voltage. And I should be careful. The change in potential energy would be Q times the change in voltage. So the idea is from this graph, we can do force problems. We could do energy problems. Why? Because both of these things, ultimately, the force relates to the voltage change. And the potential energy or the change in potential energy also relates to voltage or voltage change. This is a big deal. If you're trying to design a new type of semiconductor circuit, you're going to have a bunch of voltages running around in the circuit. That's what that last picture was. It was showing different voltages at different points in the circuit. And if you want to know how it performs, you need to know how electrons in the circuit would perform as the potential difference changes around all over, or the electric potential. Now, the first thing it asks is 24.30a. Over what interval or intervals is the electric field zero? So part A, when is the electric field zero? So let's look at our toolkit that we have here. If I want the electric field to be zero, I look for zero slope. All right, so let's hit it. There, and there are the regions where electric field equals zero. And since we're going in the x direction, I could say the electric field equals 0, or I could just say E sub x equals 0, because again, this is a 1D motion problem. Again, we're not talking about charges moving up and down. We think about them that way, but really they're just moving left or right along the x-axis. Okay, so this could be like a piece of semiconductor that's been built in a certain way to cause this situation. Happens in the real world. Okay, this might be a solar panel, right? And the idea is maybe sunlight comes in and gives an electron just enough energy to get over here, and you get a current. Okay, so yeah, anyways, that's how this might work. All right, so that was part A, the regions of 0. Hopefully that's okay. If I want 0 field, look for 0 slope. Over what intervals does the electric field point in the I-hat? So in this case, I got to be careful here with the minus sign. I know that, let's emphasize this with the color. I know that I need, if I want the electric field to point I-hat, I need the slope to be negative. So this, let's do it with a different color here. That region has E sub x greater than 0. Here's how my analogy works. If I think of putting a marble here and letting go of it, the marble would roll down the hill. That's, in a sense, increasing the x coordinate. So that tells me the direction of the electric field, which way a marble would roll if I let go of it. So if I put a plus charge here or a marble here, it would go to the right. We think of it as rolling that way. All right, next, and checking. So far, so good. Speak up, unmute anytime you want, or throw it in the chat, okay? Part C, I'm gonna look at part C now.
I just want to be like super thorough
Yeah,
with
yeah, yeah,
something.
do it.
It's correct to say that my reasoning would be to look for the negative slope, because that negative slope would cancel out the negative in front of the dv over dx.
Yep. If I want this to be positive, the slope needs to be negative so that it cancels that minus sign.
Okay.
Yep.
Okay, cool.
And obviously, if we wanted this thing to go to the left, well, that would be right here, agreed? Because this would be a positive slope. When you plug in a positive number, this flips it, and the E field is negative.
Okay, cool.
Good job. Good job. Okay, part C. Let's just stick that up there in case you've forgotten. Where is it? Part C, this one. It's initially located at the origin, traveling to the right. What is the, okay, so I'm going to write this down. And I need some more room, and I'm going to just scoot it back just a little bit. What did it say, a proton? So part C. If the proton is sitting at the origin, what is the voltage? The voltage is 20 millivolts, right? And how do I get the electric potential? Or sorry, what did I ask for? The initial potential energy is what I asked for. So this is not the answer. I need to get U. Was it a proton? I think it was a proton. Proton. So that's going to be 1.602 times 10 to the 19th. Oh, that's, I'm running out of room. That's the charge, right? So that's the charge times 20 millivolts. Where this is the number 1.606 times 10 to the negative 19th. So I'm going to punch that in, and I get that number. Oh, and let's check the chat. Not sure what you mean, Sean.
Oh, I was just looking at the equation sheet and noticed that there was one exactly like that one on the board.
Yes,
just with
that's, I think the other one, do you see that's got a subscript C?
Yeah.
That means capacitors.
Oh,
So,
okay.
so Sean is asking a great question here. He's looking at this one right here. He's like, dude, what about this 1/2? That is useful if you have capacitors. So that subscript C means capacitor. Great. Is that good on that?
Yeah. My bad. I didn't know it was ahead.
Yeah,
of
no. That's the next chapter. So we're setting ourselves up for how to deal with capacitors. The 1/2 is a lot like the spring force and the spring energy. When you integrate it, you get a factor of half because there's a blah, blah, blah. Anyways, same kind of thing happens with capacitors. They're like springs. Anyways,
Right.
all right. They store energy. Okay, good. Great question. Sorry I didn't address that sooner. Yeah, and so at this point, you punch in some numbers, you got it. You've got the answer key. So let's go on to part D. So if you want, you could punch that in and check it. You should check it. You should definitely get good at punching in the numbers because you know what Canvas is like. All right. So let's see. What's the next one? Oh, this is a good one. Let's see if we could actually understand this. What is the minimum initial speed for the proton to reach that end position? And now you better pay attention. The idea is, I need to erase some stuff. Let's get this clean again. I have a proton. It's sitting right here at this spot. I want the proton, sorry, there we go. I want to get the proton from here to there. Now, in practice, it's not going up and over the hill, right? It's really just moving horizontally, but we want the proton to end up over here. So think to yourself, where is the proton going to run into trouble?
At the top of your hill there.
At the top of the hill. So it's not just enough to get it from here to this height, because if you get it up here, it's just going to roll back down. So that's where the marble analogy helps a little bit. Again, this thing is not going up and down. It's going left, right, but it's not going to get up and over this hill in our mind unless it has enough energy to get up here. How
Just
fast?
use a negative charge.
There you go. That would be much easier. So, but in this case, if we want this to get to here, it said, what is the minimum initial speed? Based off that statement, if I say the minimum initial speed to get over here, how fast do you think it's moving up here at the top? Fast or slow?
Slow.
Slow. And so we say at the top, we'd say the speed is approximately equal to 0. It only needs to be going a tiny bit faster than 0 to get over there, right? Now, notice something right now. There's V, which I'm drawing as a capital V, and there's V, which is a lowercase v. You got to keep it straight. You figure out what you're going to do, and I'll jerk and notice that the computer's lagging and get tripped out by watching it on Zoom. So now, in this case, my way of keeping track is a capital V. I will do these little serif on there, these little toggles on there, and a speed is a lowercase v. And so to be consistent with that, I'm going to try and do that up here. Now, these are units. There's units of V as well. So you've got a lot of V's. You find your own way to keep track of them. I recommend anytime you have a voltage, make that a capital V. And this is one thing you could do. I think it's worth the extra effort because I get confused a lot with all these V's floating around. So you can see I've tried to adhere to that in most places, and I do screw up once in a while. You will too. Lowercase v is speed. And there we go. All right, so now to set this one up, let's go ahead and hit it. And you may have already finished it. I need to erase here. What type of problem do you think would be best? Should I do forces and kinematics?
Energy.
Energy would work. We could do forces and kinematics as well, because notice this is a constant slope. It's a constant electric field. So it's a constant force. So it's a constant acceleration. You could do it either way, but I hope you agree energy will be faster when you see it. So basically writing that down, I'm going to say that delta K is equal to negative delta U. For some reason, when I do these types of problems, I usually do the delta U's because I look at changes in voltage, and that's what matters in a problem. If you don't like that, you could also just say K initial plus U initial equals K final plus U final. Either way will work. So I'm going to try this one. Whoops. And this is why I kind of like this one. The idea here is it's really easy to read changes in voltage. So the delta U side becomes pretty quick. It's just Q times delta V's. Not that the other way is any different. It's just plug in numbers. This is exactly the same. It maybe takes one more line of algebra. So if you really like this, do not just change over. That's a great strategy for success. Now, in this particular case, one of the biggest things you got to worry about in these problems, as you know, are minus signs, right? So there are a lot of minus signs. In this particular case, what is the initial point and the final point? Well, I know this is the initial point I care about because that was the one told to me. And you told me that this is the trouble spot. So that's the other spot. As a result, even though we're going way over here, I worry about this point, and that tells me that this goes to 0. Now I see that this minus sign and this minus sign cancel, and I rewrite because it's getting out of control. And if you don't take your time on these in the sense of working it out on paper, you are going to miss a minus sign and you're going to screw it up. So, all right. So now what am I looking for? V, I think, right? And they all end up looking the same if you start to do them this way, and then you get really fast at it. So if you don't do the practice, you'll be slow. So I'm going to get two Q delta V over M. Two M. Yep. Now, just be aware. Sometimes it's not going to be this simple. Sometimes there'll be other terms in there because sometimes you'll actually have a final velocity, right? And so don't expect this to always be this easy, but it's usually going to be this easy plus or minus this term. So you might get one more term inside that square root sometimes. Now, in this case, I'm going to erase this one. So now I know that the initial here, which root makes sense? Well, this thing's moving to the right. I'd expect I need the positive root, so I'm not even going to worry about this. So again, because this thing is going to the right, I would use the positive root. If I asked for initial speed, did I ask for speed or velocity? Speed. Sweet. So it doesn't matter anyways, right? So if I ask for speed, it's always going to be positive. Well, now it's just numbers. You could check the units. Let's worry about that later.
I've got a quick question.
Yeah, sure.
If we started at 200 nanometers, which would be the first spot at the bottom of the hill, it wouldn't change anything, correct?
Absolutely correct. So the question was, if you started right here at 200, shouldn't it be exactly the same? You bet. Just like, what if we only went to 950? It would be exactly the same. Now, what is lost? There would be something different. The thing that would be different is the time it takes to get over there. But we don't care about that in this question. So there are going to be some differences if you start at a different spot in terms of how long it takes. Is that good?
Yeah, thanks.
Nice. Good question. All right. So what is delta V here? I need to go from here to here. So is it positive 60 millis? Because I went up 60 times 10 to the minus 3 volts. Watch those prefixes. 1.67, what is this, times 10 to the minus 27 kilograms? Let's make sure I didn't screw that up.
Just to be safe, we could also just say, since it's the difference in voltage, we could say the final volts minus the initial volts, right?
Yep, absolutely.
Okay.
Final volts minus initial volts. And I think I said this has a 3 in it too. Okay. Yeah, so, and again, as long as you're careful keeping track of V initial, V final for speed versus V initial, V final for voltage, you're good. And keep track of your minus signs, you're good. And notice we don't have to do any R hats or R vectors. It's pretty sweet. And then at this point, you plug that in and the answer's in the book. So I'm going to go ahead. I think we've actually finished this whole problem, and maybe we could take a look at it and see if there's anything in the solution. Oh, there's more in the chat. Let me see what that is. Okay, cool. And yes, Corey, if we were talking about circuits, that's a different issue. However, Corey, in the vast majority of circuits, the resistance in the wire is negligible to the point where it wouldn't matter that much, because most of the resistance in a circuit is going to come from stuff other than the wires. There are significant exceptions to that. An alternator in your car, or I don't know. Yeah, so right, that's basically all wiring. Right, or for a transformer, right? So there are cases where, let's leave it at that. We'll talk about all those later in the semester. All right. Is that cool, Corey?
Yeah.
Yeah. For now, basically ignore that, and we will talk about that 2 chapters from now. All right. Cool. I'm gonna just quickly share the screen, and then after that, we'll probably take a break. So let's see if there's anything else in the solutions that kind of jumps out at you. What is this, 24.30? There we go. And so blah, 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 blah. And so verify you're comfortable with this. So this is, again, this analogy, it's not perfect, but it does help me a lot. I think about it every time I do this problem. So, so there we go. I think we talked about all of this stuff. And then, yeah, so this is the other thing. People forget about, so we got the initials and the finals. We got the minus signs. We got to worry about V versus delta V. And we've got to worry about units and prefixes. In short, this is an engineering problem where you have to get a lot of details right. Remember here, just to be clear, I should mention this. E is not the charge of an electron. E is the magnitude of the charge on electron. So E is positive 1.6 times 10 to the negative 19th. So remember that. E is the charge on an electron magnitude. So that's positive.
Why are we considering the magnitude and not the actual positive or negative?
Well, so we are considering the positive or negative, but because it's a proton, it happens to be plus.
Oh, okay, I see.
You are absolutely right that we should consider it. If this was an electron, it would be a very different problem. I could ask you that right now. Hold on. Let's look at this. If you wanted to do this problem with an electron, think. If I wanted the electron to get from here to there, what's the minimum initial speed I need?
0.
Basically, anything above 0, it'll be slightly creeping and it'll go, because it'll speed up and then go over. So you could kind of think of this as, imagine you had a bubble here, right? If you just push the bubble slightly, the bubble would float up to the top and come over here and get there. Whereas if you had a, I don't know, a pebble, right? It's going to have to roll up and over, or a golf ball or something. Yeah, it's going to have to roll. All right. What do you think?
I do have one question.
Yeah.
If we are talking, looking back at the graph there, if we did have the negative charge and it's making its way up, at the point it gets to the top, it would have enough energy that it would make it back down to the 40.
Absolutely. Well, remember, if it's coming here, the electron coming up, it would be moving really fast, and it would go through this really fast, and then it would start slowing down, but it would still be moving here, right?
Okay, so now let's say that our negative slope there goes all the way down to 0 volts. It would never make it all the way to 0 volts. It would only make it back down to 20, right?
It would do that. Yep.
Yeah. Okay.
And so what you see is the kinds of questions you're asking. I gave you every single variation for a negative charge and a plus charge on the rest of this page. And then I gave you guys some hella hard graphs on the quiz. And so the key is, you got to remember there's going to be peaks all over your quiz. You got to use this analogy to think, if this marble is going to get through there, it has to get over the tricky spot. So you have to figure out the tricky spot. Now, why is that? If you look at this in chemistry, there's all kinds of these activation potential plots and such like that. That relates a little bit to this, where you have to make sure you have enough energy to get over the hump, to get the reaction started. Or in electrical engineering, do you have enough energy to get the current flowing so that your output current is non-zero and you get current out of your solar cells, et cetera? So these things happen a lot. And you could imagine electrons are normally the things traveling, right? So you're more often thinking about these bubbles moving around than you are thinking about protons. Electrons are more common. So it's easiest to start by thinking about protons, and then you layer it in and see if you can flip all the logic upside down. That was a long-winded answer. Sorry. Did that address your question?
Perfectly. Thanks.
Right on. Right on. Any others?
Yeah, I have a couple questions.
Yeah, do it.
The first one is, you're not gonna make us do kinematics with these on the test, are you?
That's a yes.
Well, like I said, there are times when you could do it with kinematics. Usually the types of things I ask about are speed or force. And then that means you don't need to do kinematics. But imagine you did a problem where you already figured out the force and you know the mass. Wouldn't it be really easy to do kinematics? Yeah. So, but I got to say, I don't think so, Ryan.
Okay.
I just don't want to tell people that you can't do that way. Now,
Right, yeah.
usually it's better to do energy because not every graph is perfectly split into linear sections. So in that sense, I think this is the way to do it, and I would always do it that way. I would not use kinematics for these problems, even though in this particular one you could do it. It's just a lot more time consuming. Is that good enough?
Okay.
I don't think you have
but
to
you're
do
not going to ask
kinematics.
for like time, are you?
I don't think so. No.
Okay.
And I don't
cool.
think I asked that on any of these on this entire page.
Cool.
Thanks for the
the
idea
other
for
thing
next
is-
year's class.
yeah, next year. Make sure it's next year, right?
Yep.
The other thing is, can we go over units on part C and D? I don't know. I think I just need a
You're
solid,
right. I forgot to talk about that.
unit
Okay.
check and kind of make sure I understand all that.
Absolutely. That's a great thing to talk about. So let's take a look inside of here. So I could tell right here, you probably know this thing right here has units of what, Ryan?
Kilograms times meters per second squared. So Newton.
Sure. It's also,
Energy.
yeah, which has units of, it's a real gem.
Oh,
Joules.
joules. Yeah.
Yeah, it's a real gem of a unit. It's a joule. All right. So just tell me right now, this is units of, okay, so I need some space to work. Is it okay if I erase this number here? Well, actually, we need that. I'll go down low. I think I have just enough, right? Do you agree? I know that U is equal to Q times V. That's one equation that we have, right? So far, so good, Rye?
Yeah.
Okay. And do you agree that this is in joules, this is in coulombs, and this is in volts?
Mhm.
So didn't you just tell me that C times this should equal a coulomb times a volt is a joule. So this is actually a joule per kilogram.
Okay.
But it's the square root of a joule per kilogram. That's the units up top. Are you okay with that being the units?
Yeah.
And so then what's another unit for a joule? You were saying it earlier with newtons.
Joule is just Newton times a meter.
Right.
Right.
Which a Newton times a meter is a Newton. Well, let's just do this in steps. That's a Newton times a meter divided by a kilogram. Well, what's a Newton?
Kilogram times meters per second squared.
Right.
Oh, so
And
kilograms will
it's like
cancel
an
out.
mg. It's like an
Yeah.
mg, right? So you do have a kilograms in there to cancel out. And I was going to do that and I totally forgot. So I really appreciate you bringing that up.
Interesting.
And then, like he was saying, excellent question. So you could see how important it is that we use the right units and get rid of those prefixes. So the kilograms drop, meters squared per second squared, square root is, got it. meters per second, right?
Okay.
We get some really weird units later in the semester. I mean, weird. Like an ohm, what is it? An ohm farad is a second. So yeah, we'll get weirder units later. So the thing that he is asking about here shows up more and more as we get into these weird technical chapters later. So it's really important to always be thinking about the units. That was a great question. Thank you for bringing it up. All right. How about we take a break? Oh wait, I'll pause and see if there's any more questions before. That was all good stuff. All right, let's take a quick break and we'll come back at about 6 o'clock and try and do another one. And then maybe I'll give you some insight into those last chapters too. So, all right, let's take a quick break. All right. So a couple of things. I was just getting some simulations ready to show you, so we're not just always doing boring work. A couple of things. I'm going to throw something in the chat here for you. So I did check the next chapter quiz, and what I told you was true in terms of. Oops, wrong book. The content that is discussed on pages 78 through the end of the chapter is not on the quiz, but again, you should still learn it because it could show up on the final. And there's some reasons you might want to see that. So we'll discuss that at the very end today and kind of cover the highlights of that. All right. And you can see that this graphing is going to be a big deal on the quiz. So I expect you to know this inside and out. And yeah. So there's that. And then, yeah, there's going to be one question with integration and one question with the point charges. So basically kind of a nice mix of everything in this chapter. It's all pretty much there. So that's the quiz. And let's go ahead and I want to show you some stuff. We were talking about this stuff and trying to visualize it. Gosh, it would be nice if there was some way to see this thing moving and animated, wouldn't it? Gosh, if only somebody had coded it up. So here's a simple version of this. And I'm going to use the custom attraction just so I can see this a little bit better. The idea here is we have these two atoms, and depending where they sit, now this is not exactly the same thing, and let's point out the reasons why. This is potential energy, so that is the symbol U. But if you have a positive charge or a positive ion, remember that's like Q times V. So this is very similar to what we are doing. And depending on how this thing is oscillating, right, and depending on, in particular, the interaction strength. So notice as I'm changing this arrow up and down, I'm changing the size of the potential well. We see it changing. I'm changing essentially the interaction strength. So I'm changing how strongly these things interact. And if I could run this in slow motion, the idea here is we're trying to show the behavior of this thing as it goes back and forth. And so again, I want to clearly indicate, let me pause this for a second, sorry. We have a marble that's shown here. Oh, come on. So this little marble here that I'm pointing at right there, that marble right there is rolling back and forth. All right, now that shows this thing moving up and down, which gives us a feeling. Obviously, as this marble rolls higher up, we expect it to slow down. So this is analogous to a positive charge. So we're assuming this is a positive charge right now, okay? So when it goes higher in potential energy, that would be like going to a higher voltage and it slows down, all right? Let me get rid of that. Come on, where am I? There we go. Sorry. So, and furthermore, if you play this thing in slow motion, think about this. Where is it going the fastest? When you move it up here, it's going to be slow at the top. It gets really fast, and then it's going to move slow as it goes up. So if I work this thing, let's move it up higher here. Now, the actual motion of the molecules is not up and down. Watch the molecules themselves down here, and you'll see this molecule is moving in and out. So when we run this, this thing moves, and notice it goes really quickly through the bottom. And so it actually spends most of its time far away. So if you really wanted to understand the time, gee, it looks like you would code this up. And then we could also do stuff like this. We could change the diameter of this thing and see what happens. And as we run this one, now you can kind of see it a little bit better there. And every different atom combination is going to have different sets of these things. So different covalent bonds are going to cause these things to do different things. If I show the forces, right, you can see what's happening here. If I pause this at any given second, the attractive force, or van der Waals force, is right here. So these are attracted to each other. And then the repulsive force is this one right here. from the electrons, the Coulomb force, basically, right? And so that's trying to push them away. When you get the electron clouds too close to each other, there's this massive repulsive force, and that's what gives rise to these curves of potential energy. This something similar would happen in what we were just working on, where we talk about the voltage, right? You might see these weird shaped voltage curves because of the way you design your semiconductor microchips. All right. Now, and then one last piece here. Notice this thing is pinned in place. This is totally artificial. In reality, these things are going to be spinning around, and they're going to be orbiting and moving and doing some complicated motion, but they will have some, this is so, to simplify it, we think about this as being a 1D motion problem. There's that. Any questions on that? Just checking. Oh, and so those atoms were interacting. Yeah, we're thinking of this as, you could think of the nucleus as being a positive charge and this electron around it. And where it gets complicated is when it's near another atom, the electron cloud might get shifted, and you actually can treat these molecules as a dipole. And so, yes. Or would it not ever? Oh, Tom, I didn't see your question there. I'm sorry, I missed it. Would it dampen out so it sat at the bottom of the energy well? Oh, what would dampen it out? Yeah, so eventually what's happening is you could imagine light could be radiated, right? And so this molecule could store some energy, or you could convert it from translational energy to rotational or spring. So there's different forms of energy that it could be transferred into. Now, I would think the most common way to get rid of some of that energy would be for this thing to emit light. And that relates to quantum mechanics and physics 162. That is not the subject of this course. Some of you already know about that. And so, Tom, does that kind of address that?
Yeah, that makes sense.
Emitting light. And it turns out one particular subject in chemistry talks about the types of light that are emitted by this large vibration, and those energy states are quantized. If you probably know about that, right, Tom? Because you took 162. All right, got it. Okay, so that's cool. Let's look at another example here. Hold on. Wait, there's more. Let's see if I get it right. This one. So you know I love this one. Let's go into here. This is supposed to be a simple version of this, where you could imagine we had the problem that we just did, where maybe something comes here and it's coming in, right? And so then it kind of went up to a really high point, and then it kind of stayed there. So I'm trying to simulate what we just did a minute ago. And then didn't it come down and kind of go to a lower spot? So this isn't perfect, but if I just put one more in here, I could probably make this look a little bit better. I don't want to spend all day trying to make the simulation look perfect, but the idea might be something like this. Your curves on your graph look disturbingly similar to this mess. Anyways, yeah. So imagine you put this skater here, and I'm going to get this skater going with some kinetic energy. I'm going to slow it down. And so right now, that is supposed to be a model of this, right? Somehow the skater gets to here, and somehow the skater is moving. This is a proton with some energy. We want that skater to get up and over this hill and just barely get there, right? So if you wanted to watch that one, this is a simulation of that. Let me get back to it. And so again, maybe we don't know how it got there. Maybe we didn't see all of this stuff over here. So imagine that's not there. The point being is this skater is moving this way. It's going to slow down on the way up. It's slowing down. It's slowing down. It's slow. Oh no, it didn't have enough. Oh, because the it's too bumpy down here. So sorry. Let me see if I can smooth this out a little bit. All right, let's try this again. So I'm going to start this up here. Whoa. All right, so now somehow that skater is right there, should slow down on the way up, slow down, should just barely get up there. Oh my gosh, really?
I think
It's
you have
because you
friction
have
on.
friction.
Oh, do I? Oh, sorry, the chat box was blocking the friction. Thank you. All right. All right, let's try this one more time. Thank you for checking that. All right, so again, starts here, slows down on the way up, slows down, and then we see it get over there. And so, yay, great. That's supposed to be a simulation of what we saw. And if you look at the energy when this is doing this thing, let's go back here and run it. Should have just enough to get over the hill here. We see we're converting kinetic into potential. So it's all potential down there, or almost all, or sorry, all kinetic. Right at the top, oh, you can't see it. It's mainly potential, but there's a little bit of kinetic there. But we see that the mix of kinetic and potential, it doesn't ever have to be all one or the other. All right, and I think that's pretty good for that one. So let's leave that. And finally, one last piece about this. Why do you care about this? My apologies if this is boring you. Oh, I thought I brought that up. Oh, no, no. Where is it? All right, let's just run the, oh wait, not that one. This one. Ah. Come on. Oh, come on. I thought I'd opened this when I was on the break and I didn't. All right. But the fact remains is I'm just going to zoom in and give you an idea here. My apologies. We only need the screenshot for this one because we're not going to be playing around with this one. I just want to point out that what do you do in modern physics? Notice there's an energy diagram here. And you can't really see this, but there's position. Maybe if I move my crap away. So the idea is there's position versus energy plots that show up in this field. And this relates to atomic energy transitions and light and things like that. And this furthermore relates to semiconductor devices like diodes or transistors. So this shows up in a large number of things. I think I've motivated that enough. The fact remains, it's important to know this. It's on your quiz. Make sure you do a good job on this because I think it's hugely important, especially for electrical engineers and physicists. All right, that was what I wanted to emphasize with those simulations. Any questions on that? All right, appreciate it. We're going to have some time to do more questions, but I want to make sure I at least hit the highlights of the end of this chapter so that you know why that other stuff is important. So let me do that too. I think you could do those other 3 problems at home. So again, make sure you do a good job on the rest of these 3 problems. You can see that here's an electron. You got to watch your minus signs, and it starts from rest. And now notice here's one where it starts, where it gives you the initial speed, and then you can see what's going to happen. And these ones start to look a lot like your plots on your, and everybody has different units, and everybody has different peaks and valleys. Everybody has different delta V's, but it's all the same procedure as long as you get used to the units. So make sure you do these, all these, same thing with an electron, etc. Okay. Now, that is going this way. We just talked about if you have voltage, you could take a derivative or get the slope and figure out the electric field. The other thing is you could actually start with the electric field, usually from Gauss's law. What? So you could talk about the electric field from Gauss's law and use that to calculate voltages. Now you may be saying, this is stupid, dude. There's no use for this. That's fine. You don't have to be an electrical engineer, okay? If you want to be an electrical engineer, this is probably worth doing. If you're going to be a physicist, you should probably understand this. Some useful info here, blah, 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 blah. Let's motivate this first. Okay, here's an example. I show you how to do the math. You can follow the examples later. Here's another example. I show you how to do the math, right? And this is a big deal right here. Okay, so this shows you, I kind of walked you through the examples there. It should be just kind of follow it. It's not that crazy, but yeah, in this case, I see 2 pieces of metal. This one's got a positive charge. And over here on this one, let's cover over that with blue. This one has a negative charge. There's a name for this object. Does anybody happen to know what this object is? 2 metal plates separated by a small distance with some charge on them.
Capacitor?
This is a capacitor. It turns out in physics, if you want to understand capacitance, you really need to understand this problem. That's very cool. Now, I'm going to be honest with you. If you have to skip something, skip this one. Skip 24.35. And I think somewhere I have the equations written down. Let me make sure I didn't ask you to do those. This is what, chapter 24? What problem is this? 35? Yeah, good. I left it off. So your list is already accurate. I told you not to do this. If you're a physics major, you could do it. These are really hard. This one's still pretty good. I gave that on a test once, 34. So this might be something you might study for the final or something. All right. Blah, 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 blah. A bunch of words. Fine. This is another example. I want to point this out. You got a negative charge and you have a positive charge here. Does anybody know a name for this device? What this is? Imagine you have two long lines of charge separated by a small distance. Imagine they're made, it says conducting.
Like a taser?
This is not a taser, although that's interesting. It kind of looks similar to one. I could see how you'd think that. Not a diode. Let me help you out. This is a different capacitor. There's different types of capacitors. So what are we going to do in the next chapter? Looks like Python. Oh, okay. So let's not do that. Let's keep going. I'm just going to show you the next chapter. Blah, 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 blah. What are we going to start with in the next chapter? Capacitance. What are we going to do? Get the electric field using Gauss's law. Do an integration to figure out the voltage. Why? Capacitance is defined as the ratio of stored charge to stored voltage, or to voltage across. You don't store voltage. Okay, so stored charge to the voltage required to store that amount of charge. There's one case. Here's another case. Spherical shells. This is used perhaps in, there's reasons for that. I'm going to leave it at that. Here's the coaxial cable. So we're going to start getting, and here's power lines. If you wanted to know the capacitance between those. All right, and then we'll go into circuits. So that's where we're going in the very near future. So it will be very different soon. I just wanted to motivate that last bit of the chapter is designed to help you understand the next bit of the next chapter. So do what you got to do. You could decide to study that next week after the quiz, or you could study it this week if you have time. We have 15 minutes left. I've covered everything. Do you want to do another problem maybe? Or do you want to work or what? Okay, another problem. Do you want to do another graphing one? How about we do one with an electron that's moving and just get it set up? I think that's a good idea. That'll be a little bit of a variation, okay? So let's go back there and see that. I'm pretty excited about where we're going, and I think you will have more fun too. Regarding labs and lab partners, I think I figured out a way where we can help you guys pick your own lab partners, but a lot of you don't know anybody in class really because you don't have any way to talk to people in lab anymore. So if possible, try to start figuring out who your lab group will be in groups of 3. And we could try and make this a little bit less solitary. It's going to take some work on my end, and I don't know what work that is. I'm very confused by it, but I can't use Discord because of ADA compliance and such. But yeah, we can. Yeah, so I know you can use Discord to group up as groups, but anyways, let's get to this. Let's start right here, and I'm not sure what this problem is. So start right there, 24.32a. We're going to take a charge and release it from rest at x equals -10 centimeters. And I want it to move to the right. Would we have to use a plus charge or a minus charge? What do you think? You put a charge right here and you want it to move to the right. What do you think?
Positive.
Positive, because remember, negative slope means electric field is pointing this way. greater than 0 for slope less than 0. So let's not do this problem and save that for you later. I want to do one with a negative charge, right? So, okay, that was cool. I didn't know. Let's go to the next one. Oh, same plot as the previous question. We have an electron initially at 50 centimeters moving to the left. Okay, this has got a lot of minus signs. This is perfect for us. We've got an electron sitting right here, and it's moving to the left. So I'll call that V0, and that's a velocity, not a voltage. All right. What are some things I need to look at on this graph right away? Units and prefixes. I'm just keeping an eye on that, all right? So next up, what initial speed is required for the electron to reach positive 5 centimeters? So that's right here, right? So what do you think? Is it 0 or is it something? That's what I need to know. Remember, it has an initial speed moving to the left. Oh, go ahead.
It's something that has to get over that, or under rather, that valley.
Exactly. So because we're thinking about electrons right now, think of it as a little bubble. Bubbles don't want to go down. So you're going to have to give it some kick. I think that was Trey. I might as well put you on the spot, Trey. Where's the trouble spot? Where are we going to run into trouble?
At 40 centimeters.
Yeah, exactly. So right in this region, right? So based off that, Trey, let's just keep rolling. What do you think? What should we do?
Pretty much the same as the last problem, but different. Or not different, but opposite, where we start off with the potential energy currently, and we need to find Q delta V.
Yep. All right. So let's go ahead. So go ahead and use that information. I'm going to write up some stuff on the board too. You've got it in front of you. And I need to erase. And it's not always finding the initial speed, but that's a common one. The other common question is, let's say you started here from rest, what is the final speed? Those are the two common questions, right? Or how much speed was lost, et cetera. You start at some speed, and what is the speed at some different spot? So or, you know, I'll do this one the other way, just so we get a mix. In this case, I'm just going to keep writing. And oh, what problem are we doing? 24.33, right? I have to be careful now. I used U, and that relates to Q times voltage initial. Because this is U initial, not delta U, I do not write a delta V. So there's two styles. The last one I showed you delta K equals negative delta U. Here I'm saying initial energy equals final energy. In this problem, somebody other than Trey, what is Q?
Be the negative 1.602.
And are you okay if I just say negative E?
Yeah.
Nice. And so what else? Is there one of these things is probably equal to 0? Which one? Somebody other than those two people.
V final.
Okay, so V final is equal to 0. All right. And that's because we're just barely able to get it. The problem asks for the minimum speed to get over to that other spot. Okay, so that's good. So that's going to take care of this crap. All right, and somebody else. What's V final? And notice I deliberately tried to be annoying there, right? You just told me V final 0, but I want V final. Remember, there's two different V's. All right, that's all I'm trying to do. What's the initial voltage?
10 microvolts.
10 micro. Yep, 10 times 10 to the negative 6th volts. Nice. And then the final voltage is Where was it going to? 5. So that is going to be what? -10? Wait,
-2.
-2. I was reading the wrong thing. And obviously keep all the sig figs for a canvas problem. Generally speaking, unless otherwise specified, we assume at least 3, 4 on this. So yeah, I'm ignoring sig figs here. I think at this point,
wouldn't it be -6 since it has to get over the valley pretty much?
oh shoot, you're right. I fell into the trap. Hey, remember this on quiz day. This is the final voltage. You're right. However, that's not the final voltage where the speed is 0. This was totally wrong. And now you know this is the common mistake on this question, and we fell into it. So thank you. That was absolutely wrong, and it's good that we caught that right now. The trouble spot was at 40, where it's what, -6? Thank you, Trey. Does everybody see that? I'm going to screen share to make sure we got that. And now we know, and you can see even me who made this stupid problem still screw it up once in a while. So you got to watch out. It starts right here. This is the trouble spot where the final speed equals 0. So that's the spot where we need voltage final. -6, right? And just to be
Can I ask
clear,
a really quick question about
absolutely
the setup? So like, let's say you said, what would the speed be for it? Like, let's say if you wanted it to reach, let's just say like -5 on the x-axis, so like -5 centimeters, because then you're gonna have to get past 2 valleys. So like,
yes,
right?
but which is the hardest one? The deepest one.
So the deepest. So if you have
So
enough,
like, let's say I said, what is the speed required to get to this point? Well, you'd still go to this valley because that's the hardest part for the air bubble. The air bubble has trouble getting down to here. Once it does that, it speeds up, it slows down, but it doesn't stop. It speeds up.
so it would still have enough.
Exactly.
Okay, gotcha.
Where it's sort of like this one. Yeah. Is that good enough on that?
Yeah, that's good. Thank you.
And we could show the simulation in a minute what that looks like, okay? So when you get these double wells, basically, if you get over the hardest part, you always want to look for that. And so now we see the issue. At this point, I think the problem is easy. Oh, wait, what's the mass?
9.109.
Yes. Remember that this is the mass of an electron now. So they don't have the same mass. So you always got to be looking for this. What is a coulomb times a volt? Remind me. It's a real gem of a unit.
Joule.
Joule, which is a Newton meter, which is a blah, 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 blah. Okay. Kilogram. Let's just do it. Right. So, and just as a side note, from a practical standpoint, when you're punching these things in, I know I probably said this, but I'd rather do it again just to speed you up, right? The idea is if you use the EE button for your prefixes, wherever it is, right? So if you had like, it's 10 EE -6, so that's 10 microvolts. So it's just quicker to use the EE button all the time. And then remember, there's a difference between the minus sign and the negative sign on your calculators. But you guys probably know all that. But I just rather make sure I say it just in case. So if you get used to using the EE button, that handles your prefixes, and then you don't have to write it out. You can just use the EE for the millis and the micros, et cetera, and the nanos. All right. What do you think?
Very similar.
Yep. Let's look at part B really quick. I think at that point, I know you can do that. And I know a lot of you are going to want to do that, but let's take a look at part B and see if there's something tricky there. This is a good question to see if you understand the concept. If it's slightly greater than that minimum speed, what should happen? Travis, I'm going to pick on you, all right? Because I know that you were kind of talking about this. Let's see.
Yep.
And I'm not trying to embarrass you or anything, all right? I just want to see. All right. So could you describe, let's say the initial speed ended up being 20. Let's say you're going 21. So you're a little bit faster. What do you think would happen? And let's start with the electron right here. It's sitting, let's say the electron is sitting right here. It's going to move a little bit. When it gets to this spot, is it going to speed up or slow down? What do you think is going to happen?
I mean, if it's an electron, it should speed up, right?
Speeds up to right there. Now what's it going to do?
It's going to, over that, it shouldn't move, right? Because it is zero,
but now we're just slightly bigger, so it's just barely going to have a velocity. So what should happen?
It'll slow down.
Slow down and be barely trickling along across here, barely moving, right? Okay, so then what should happen?
Back up.
Okay, speeds back up. It's going towards positive voltage. Then right here,
it'll barely be moving.
No, it'll be moving quickly.
When it gets to the top,
like let's say this was 20. Let's say 20 was the number. If this was 21, maybe this one down here is like 6 or something, right? It'd still be moving pretty fast. And here it's like 0.1.
Gotcha.
You know what I'm saying?
Yeah.
Okay, so do you agree it's going to keep moving at a good clip? Then what?
Then it'll be slowing down.
Slowing down. And then when it gets to here,
it'll barely be moving.
It'll be a little bit faster than this, though. Do you agree? So maybe it's moving at 1.1 because it's not all the way down there.
Okay, that makes sense.
And then what's going to happen? It's going to make it through that.
And it's just going to take off.
And it's going to speed up to infinity.
Yeah. Okay.
Cool. All right. And so did that make some kind of sense?
Yeah. So then you would just do that same. I mean, if you were looking at the motion, like if the problem said moving to the right, then obviously you would just do the same procedure, just working to the right of the graph. Like it's that straightforward. I mean, because you would have to have like if you said it was moving to the right and it was started,
here and moved to the right, it would slow down, constant speed, speed up, constant speed, slow down, just barely make it through, and then speed up, speed up, speed up. Oh wait, right here it would run into trouble, right? So look, let's say we release this thing from rest.
Oh, because of energy, it wouldn't reach the top, like if it was from rest.
Oh, shoot. Actually, let me be careful. If I do an electron from rest, what's going to happen to it right here?
It would go up. So you
so that's not what I want.
So you could say, like, what initial velocity would you need to give it in order for it to, like, reach, reach there.
Exactly. Okay. And so this is where it gets a little confusing. So if we start here, it's going to slow down, constant speed, speed up, constant speed, slow down, almost stop, and then it's going to speed up and it will easily make it over there. Now, what if this was a proton? What if I did this with a proton right here? If I started with a proton here, what would happen to it as I go this way?
It's going to speed up and then it'll slow down as it's going up. And then if you didn't, and if you released it from rest, it would only get to, you couldn't get it over that hump, right?
So it would stop right here, which is about maybe like 44.5.
Because of
then it would go back.
The conservation. Yeah. Okay.
So this would look like a bound state. So this would be a charge that's trapped and it would oscillate back and forth like those molecules we saw, or like the skateboarder going over the hills, right?
Gotcha.
And so the thing that's nice is it's really easy to think about plus charges, but minus charges, we constantly have to flip it. You could literally take your paper and flip it upside down, and then it would be like the skateboarder problem, right? But then your numbers are going left, right, and it's confusing. So, all right, good. And that's probably it for today. We've got an hour of office hours. I could do more problems. If you guys want to see anything else from this chapter or whatever, we can do that. I'm going to go ahead and stop the live stream, I guess. Whoops, let me hit that.